Hello, everyone, and welcome to today's live broadcast, The Bread and Butter Method of Genomics, How to Improve Your qPCR. Presenting live from Hamburg is Dr. Tim Schommartz, Global Marketing Manager, Automation and PCR, Eppendorf. I'm Christy Jewell of LabRoots, and I will be your moderator for today's event. Today's educational web seminar is brought to you by LabRoots and sponsored by Eppendorf. For more information on our sponsor, please visit eppendorf.com. Now, before we begin, I would like to encourage you to participate by submitting as many questions as you want at any time you want during the presentation. Simply type them into the Ask a Question box located on the left and click the Send button. We will answer as many questions as we have time for at the end of the presentation. Additionally, we will be conducting a few interactive polls throughout the webinar today, and we appreciate your participation. Now, if you have any trouble seeing or hearing the presentation, just click on the Support tab at the top right of the presentation window, or just let us know you're experiencing a problem by using the Ask a Question box. This presentation is educational and thus offers continuing education credits. To obtain your credits, please click on the Continuing Education Credits tab located at the top right of the presentation window and follow the process. I would now like to introduce today's presenter, Dr. Tim Schommartz. Dr. Schommartz is the Global Marketing Manager, Automation and PCR at Eppendorf Headquartered in Hamburg, Germany. For a complete biography of our speaker, please visit the Biography tab at the top of your screen. Now let's get started. Tim, the stage is yours.
Christy, thank you so much for this nice introduction. I want to welcome everyone and thank you for tuning in. A warm good afternoon from Hamburg, Germany. Before I begin, I want to apologize for any upcoming background noise, but there has just been a construction site starting in front of my office window, and there seems to be some really important jackhammer work going on. But that's the beauty of a live webinar. So I want to talk about the bread and butter method of genomics, namely PCR and qPCR. It's a method that is very widespread in a lot of labs around the world, and I want to share some insights from the Eppendorf perspective on this very important method. This webinar should be interactive, at least as interactive as it can be, and therefore, in order to get to know you a little bit better, I would like to start with a poll. I want to know what is the main purpose of PCR in your lab. You can click as many answers as you want. So are you using PCR mainly for cloning, for example, for CRISPR-Cas or protein engineering? Are you doing genotyping, forensics? Are you using PCR to prepare your next generation sequencing libraries? Are you using PCR for quantitative analysis, let's say qPCR, or in a qualitative manner, a standard endpoint PCR? Or do you have any other PCR applications? So I see that the first answers are coming in. Thank you very much for sharing this. So I will read it again. What is the main purpose of PCR in your lab? Are you using PCR for cloning, genotyping, forensics, to prepare your next generation sequencing libraries, for quantitative analysis, qualitative analysis, or for something different? Just a couple more seconds. Okay. Thank you very much. This is really interesting. A lot of you guys are using qPCR, I can see, and then it's followed by genotyping and next generation sequencing, as well as qualitative analysis. So thank you very much for sharing this information. This helps us here at Eppendorf to further improve our products and services. Okay, so let me come back to PCR, and I think that you have seen a slide like this a lot of times. So the basic principles of PCR So you start with the denaturation of a double-stranded DNA, so you get 2 single strands, then you come to the annealing phase where the primers anneal, and you get to the extension phase where you multiply your PCR or your DNA, and in the end you got 2 copies, and by that you are multiplying your input material. So I think you have seen that 100 times, as well as the basic principle of qPCR, where you are introducing some sort of reporter. It can be a specific reporter like a beacon or a probe, or something more unspecific like an intercalating dye. In principle, it follows the same process as a regular PCR, just at the end you are measuring a fluorescence, or during the process you're measuring a fluorescence, and this will reflect the amount of your input material, making it possible to do a quantitative analysis. So what is needed for a PCR? Of course, you need some input material, some DNA, you need reagents, you need some material, some tubes or plates where you are performing your PCR, and you need some sort of thermocyclers, which is needed for a PCR. So those components are connected by a process, because you have to get all of those things together in order to get your PCR up and running. And what I think is usually very important, that doing a PCR is not something which is isolated in the lab. So there's usually some upstream processes and some downstream processes. And when I was approaching this webinar, I was really thinking what I want to present you. And I was looking into the material which is available out there, and I found a lot of webinars dealing with the input material, with the reagents, how to adjust this in order to get perfect PCR results. So you can find a lot of lists which looks like this. So how to optimize your DNA template, how to optimize your primer, how you can play around with the other additives in order to get your PCR up and running, and in order to solve your problems. So I put on my thinking cap, and I thought that, okay, I think it doesn't make sense to make another webinar presenting you the exact same stuff. So what I want to do during that webinar, I want to focus on those things which are often overlooked. So I want to look closer at the consumables which are used during the PCR process, and how those can help to improve your PCR. Of course, I want to look at the instrumentation, and I want to put my focus on the process itself. So what is the best strategy to put together a PCR, aside from choosing a polymerase or a certain buffer? So let's start with the liquid handling 101 for PCR. And if you take something from this webinar, if you just remember one thing, it should be this thing. So if you do a PCR, always prepare a master mix. A master mix is key for a successful PCR. What you can see depicted here on this slide is if you have several samples and you start with one master mix, you will have the exact same amount of the different components in all of your reactions. If you split up your master mix into 2 tubes, you will always have variability, and this variability will be reflected in your different samples. So do a master mix, and do a master mix for every set of primers that you have. So even if you have 10 sets of primers, you should do 10 master mixes. Don't try to put your reagents together one by one. So it's important to prepare master mixes. I would always account for 10 to 20% overage when you are preparing your master mix. I would use one vessel for one mix. So don't split your mix up. So don't prepare it in 2 separate vessels. the results will vary. I would always start by pipetting with the component with the highest volume, and you should add your enzymes last so that they can stay cool as long as possible. There are two other tips which I followed while I was working in the lab. So I would always aliquot the stock solutions, just in case when you put together your mix that if you do a pipetting mistake, so let's say if you go with your tip, which contains a primer, into the tube of your polymerase, that you are not contaminating your total amount of the polymerase, but just that one aliquot that you are using for this particular setup. And I would also, in the same respect, aliquot primer dilutions, so that even if one aliquot of the primer dilution is contaminated for whatever reason, you can go back to your stock, either create a new dilution or you take out a new aliquot. So a quick excursus, how can consumables help you with those aliquots? So there is a technology called protein low bind for tubes. And as you can see here in that slide, if you aliquot your enzymes in this kind of tubes, you won't lose any protein to the plastic material. So your enzymes stays intact during long-term storage. So once you've put together your master mix and you mix it through, you might experience that sometimes it can be tricky to handle master mixes. They can be foamy, sometimes they are very viscous. And there are a few tips and tricks what you can do in order to handle those things. So one option is slow and steady reverse pipetting. I will come to that in a minute. If you have like really tricky mixes, you can use positive displacement systems, and there is the option of using automation. To this I will come a little later. So what do I mean with slow and steady reverse pipetting? So regular pipetting, what you know in the lab, is what we describe here as forward pipetting. So if you have a manual pipette, you press down to the first stop, then you immerse your tip into the liquid, and then you slowly release the button. And when you want to release your liquid, you press it all the way through to the second stop. So, and by that, you're pushing out all of the liquid. So, but if you have a mix which is foamy and viscous, sometimes using reverse pipetting is the better strategy here. So what you do there is you press the whole way down to the second stop, and then you immerse your tip into the liquid. Then you slowly release the button until you come up to the rest position, and then you press the button down to the first stop. This will leave a little bit of liquid in the tip, but it helps you to handle viscous and foamy liquids. So this is a good strategy for constant and precise pipetting of more difficult liquids, meaning liquids which are not aqueous. So another small excursus on consumables, so how the right tips can help you. So what you can see here on the left is a regular tip, and on the right-hand side is a so-called low retention tip. And I think that you've all experienced that in the lab. So if you're handling a very viscous liquid, sometimes they tend to stick to the tip, and it's really hard to get them off. And this leads to a loss of final volume in the tube. So this is what was happening to me when I was working in the lab. I was preparing my master mix, and then I was putting my experiment together, and I accounted for some overage, and in the end I figured out, oh no, I'm missing like 3 samples. The reason is I was losing material to the tips. By using low retention tips, you can overcome that. And those of you more experienced with PCR, you could already see something with these tips. I would always highly encourage you to use filter tips. in all scenarios where you're working with PCR, because even the slightest traces of DNA or nucleic acids, due to the multiplying nature of the PCR process, they will be multiplied in your sample, and you will see cross-contamination. So what helps you there is a good tip quality. Here at Eppendorf, we use different purity grades. We have one purity grade called PCR clean, which are made for doing PCR, so you can be sure that you don't introduce anything with your tip. And the filter avoids cross-contamination by aerosols. So again, let me tell you a quick story from my time in the lab. I was working in a virology lab, and at some point, people from another department were coming over to our lab asking us if they can do their PCRs in our lab. The reason was that they were working with adenoviruses and they were not using filter tips, so all of the pipettes in their labs were contaminated with adenoviral DNA. So all of the experiments they were doing, all of their negative controls, they were positive at the end for adenoviral DNA. So then they've cleaned up all of their pipettes. That's also a good measure from time to time. Disinfect and clean your pipettes, and then they changed to filter tips, and by that they became rid of this problem. So don't underestimate traces of DNA in your pipettes. So I also mentioned positive displacement. So this comes into play when you have a liquid which is really tricky to handle. If you take a regular air cushion pipette, as you can see on the left-hand side, you have a piston, and in between the piston and the liquid, there is an air cushion. And depending on the properties of this liquid, this air cushion sometimes can make the handling difficult. So let's say if you have a very warm liquid or a cold liquid, or also something which is volatile or very viscous. In contrast, a positive displacement system, often also called stepper, an example would be the multipette on the right-hand side. The piston is in direct contact with the liquid, and by this you can handle difficult liquids, avoiding effects which are due to the air cushion. Okay, there are some additional requirements for qPCR, which I think you are aware of. So in order to do qPCR, you need a lot of biological and technical replicates to get reliable results. So this results in a high sample number and many pipetting steps. Sometimes you're also required to work with low volumes. In order to account for low volumes, I would recommend to either do contact pipetting, so anything below, let's say, 1 microliter, I would recommend to pipette with liquid contact. So put, let's say, your master mix first, and then add your sample, which is of low volume, directly into that existing liquid in your plate or tube. Another option is to work with dilution. That would be my suggestion, so that you dilute your sample where you need a very low volume in order to get it to a dispensing volume which is handleable. The nature of qPCR makes it very sensitive for pipetting mistakes, so you need to work with high precision. And since usually worst comes to worst, so for me it was often the case that qPCR was linked to normalization, so I had to do normalization first, and after that I had to do a qPCR, and that increased the number of pipetting steps dramatically. So if you have a scenario like this, I would really recommend to think about automation. I will talk about automation strategies in a minute, but first I want to present you a trick. I call it Tim's trick. It's not patented or so. It's just something that I did in the lab, and I wanted to share it with you, so maybe it makes your life and your qPCR pipetting easier as well. So I call it the 2-dot or 2 drops technique. So what you can see here is a very simple depiction of a well, of a plate. So what happened to me a lot of times is when I was pipetting a qPCR, and somebody came into the lab, was talking to me or so, I looked up, and at that very moment I forgot at which well I was. Did I add my sample already or not? Then I sometimes added the sample twice because I forgot which well I was. So I used the strategy with the 2 dots. So what I did first is I put my master mix at the lower part of the vessel directly at the wall. And due to the surface tension, it was sticking there. In a second step, I was putting my sample a little bit higher on the wall of the well. This enables you to see, if you look at the plate, in which wells you have pipetted your master mix and also your sample. So it's much easier to keep track of the process. And to combine those two things, you are simply giving it a quick spin in the centrifuge, and then these 2 drops move downwards and they combine in the bottom of the plate. Another relief is the use of electronic pipettes and multi-dispense mode. So if you work with regular pipetting, it means you are taking up one volume and you are releasing the exact same volume. Multi-dispense, in comparison, you take up a multiple of this volume and can then dispense several times. So this speeds up the process. This is a big relief for your hands, especially if you're already in the risk of getting RSI. So I would personally recommend using electronic pipettes for qPCR setup, or, as mentioned, automation. So, but before we come to automation, I want to talk a little bit about the vessels. So what I show you here are some very common vessels that are used for PCR and qPCR. So it ranges from single tubes over 8 strips to 96 well plates, and then to 384 well plates. So, and what I want to know from you is in what kind of vessels are you using for your PCR? Is it single tubes, tube strips, 96 well plates, 384 well plates, or something in a completely different format? Again, you can choose different answers, and I can see that slowly the first answers are coming in. So let me read the question again. What vessels, meaning tubes or plates, are you using for your PCR? Is it single tubes? Is it tube strips? Is it 96 well plates? Is it 384 well plates? Or is it something completely different? So thank you very much for your answers coming in. So it's to enforce, so the 96 well plates are in the lead, followed by tube strips, and the other things are in the third, respectively, fourth place. Very interesting. Thank you very much. This really helps us to adjust our portfolio. So I will slowly move on to the next slide. No matter what you are using for your PCR, there are some things that I would look out for. The most important thing is that you choose a consumable which has optimal heat transfer. Because the heat and temperature cycling is the most important process step of any PCR, and just that the actual device is giving you a temperature doesn't mean that, let's say, if a block has 90 degrees, that those 90 degrees reach your samples. In order, especially if you are running PCR with a fast PCR, let's say, you want to have optimal heat transfer. But especially if we talk about plates and talk about downstream methods, those of you who are working with NGS library presentation will know that you are also looking for a sturdy shape. So that means that after a plate, in this case, has gone through some heat, you don't want it to bend and warp because maybe you want to do a bead cleanup afterwards. Unfortunately, optimal heat transfer and sturdy shapes, different types of plastics have these properties. So if you have something which has a very good heat transfer, it's usually not very sturdy. And if you have something which is pretty sturdy, it doesn't have a very good heat transfer. Therefore, in terms of plates, Eppendorf invented these twin-tech plates, and they are using two types of plastics, polypropylene, if I'm not mistaken, for the tubes because they have optimal heat transfer, and the casing is made of polycarbonate, which is very sturdy. Another advantage of a very sturdy shape is that this is automation friendly, and that means if something is grabbed by a robotic arm, you don't want this arm to crush the plate. So if you have a very sturdy plate, those things are better suited for automation. And of course, you want your plates to have a certain purity grade so that your sample does not get contaminated. Okay, so again, a little excursus. There is a special technology called DNA low-bind, and this is especially important if you are thinking about long-term storage of your PCR samples. What you can see in this slide is storage in a standard plate of oligo, and you can see that you lose some oligo because it interacts with the plastic, and once you take it out of the plate, you cannot recover 100% of your PCR product. If you use low-bind plates instead, you can have a long-term storage and still have 100% recovery. If this is interesting for you, we have some more data on that. But if you think about long-term storage, I would really recommend DNA low-bind materials. Finally, we come to automation. So that's one of my favorite topics. I was working with the Eppendorf automation team for a long time. And what I have seen a lot of times in the past, that if I talk about automation and PCR, people think about this. So if you are running several 384-well plates of PCR a day, a month, whatever, it's pretty clear that people are looking for automation. But I want to show you that it's also useful to think about automating your PCR if you're working in a completely different throughput range, namely 8 strips and 96-well plates. Because the problem is when people think about automation, they mainly think about something this size, like this guy. It's massive, it's complicated, it's really hard to get it into your lab. But what I want to show you is that nowadays automation comes in many sizes. So there are other automation solutions which are just as versatile, but way smaller and really easy to handle. So what I show you here are 3 different automation solutions from Eppendorf, the Eppimotion series, smallest one, 5070, then the 5073, and the Eppimotion 5075. And they have different sizes, and these different sizes, they account for the complexity of the application, but also for the throughput. And so if you look at a PCR, which is not like a super complex application, a qPCR might be of medium complexity, you can see that depending on your throughput, there is a sweet spot for all kinds of automation, right? So you can either go for a smaller device or for the largest device, or you go for the device in the middle. And why is the size important? Because the lab reality usually looks like this. So at least this is what I know from my lab. Space is precious. Sometimes it's very crowded. So you need to have some space to put your device on. Usually you don't have an extra room to spare for automation. And this is why these devices are not massive in size. So the smallest one is just about 4 A4 letters for Europe, or a US letter size. The other ones are respectively 6 or 10 US letters or A4 paper sizes. And I apologize because I know that the popular scientific measurement of size is football fields, and of liquids is Olympic swimming pools, but I hope you stick with me that I go for A4 and US letter size in this respect. So what can automation do for you if you do PCR or qPCR? So first of all, it takes over the whole PCR or qPCR setup. It never forgets the well. It documents each and every step automatically, and it can account for all of the tips and tricks I have mentioned so far. I will lead you through that. And most and foremost, it does not have any risks. So especially if you do qPCR, if you do a lot of pipetting, changing to automation is a big relief for your risks, because the pipetting is done by the robot. So the Eppendorf automation solutions, they are capable of using different types of vessels, and this is really important because most likely, if you consider automation, you would stick with the system, with the plastics and with the reagents that you already have. So you can see here on the left-hand side that there are special reservoirs which account for different size tubes, 5 milliliter tubes, 1.5 milliliter tubes, 8 strips. So you can handle several 8 strips at the same time. But of course, automation also works in a plate format, may it be 96 well plates or 384 well plates. Automation can handle difficult liquids. So this is a screenshot which I took from our automation software. It's called EP-Blue. And what you can see here is that you can adjust all of the pipetting or dispensing settings in a very detailed fashion. But there is also the option to simply select a preset set of different liquids. So for example, PCR premix, something like ethanol, glycerol, and the system even accounts for contact dispensing if we talk about really low volumes. Of course, automation systems, they can use both pipette mode and multi-dispense mode. Basically, they are capable in doing everything that an electronic pipette can do and more. To sum it up, automation is very versatile. This is what I've mentioned before. So besides PCR, you can also do something like a normalization. This is where automation shines, actually. So if you do anything which is really pipetting heavy, you have a versatile system. First you do your normalization, then you move into your qPCR on the very same system. They are flexible for different throughput. They are accurate and precise, error-free. You get a tracking of your sample during the whole process. They can increase your productivity because it frees your time to do something different while the robot is doing the work. They prevent contamination because they have the Eppendorf automation solution. They have a full housing, and they can also be equipped with a HEPA filter and UV light. They protect you as well. It's maybe not so important for PCR and qPCR, but let's say if you're handling blood samples, that might be of importance. And of course, I think that the biggest thing is that they improve the standardization and reproducibility, because no matter who is operating the automate, the results will be the same. A robot doesn't have a bad day. A robot is not in a bad mood sometimes. So that's a big plus. And if you have, if you are, and you know that sometimes if you are doing repetitive pipetting work, this can be very tiring, and you can use this time to do much more important tasks. And let's face it, the major story for pipetting errors in the lab is unfortunately the pipette user. All right. What is very important for automation in general is that if you have such a thing, and this is where a lot of people are afraid of, is that you get something where you need to learn coding, which is really, really complicated. I can assure you that the Eppendorf systems are very easy to program. It's a simple drag and drop based method. I don't want to go through all of the details because we have a webinar dedicated just to that one. It's called Intuitive and Easy Programming of Liquid Handling Tasks with the EP Motion, where you can learn how to set up a PCR really quickly using EP Motion robots. All right. So after talking a lot about EP Motion and automation in general, I just want to know how many PCRs are you actually running per month in your lab on average? Is it less than 10 and you do this in tubes or strips? Is it less than 10 but in plates? Is it between 10 or 30, or is it more than 30 a month? And of course, it does not only account for PCR, but also for qPCR. I didn't put that in the poll here. So I can see that the first answers are coming in. So some are really heavy PCR users, while others are just doing PCR occasionally. That's very interesting. So how many PCRs are you running per month on average? Is it less than 10 in tubes or stripes? Is it less than 10 in plates, between 10 and 30, or more than 30? Okay, I think a few more seconds. You guys are doing a lot of PCR if I see that the answers are coming in, because most of you are actually doing between 10 and 30 or more than 30. That's really interesting. All right. Thanks a lot for your answers. And now we finally come to the pink elephant in the room, because you might ask yourself, what is this guy talking about all the time, about the process, about robots, about tubes and everything? So what about the cycler? So there is no PCR without a cycler, and I will talk about regular PCR cyclers here. I will not touch qPCR cyclers, but there are of course some general facts which you can take from regular PCR cyclers and also transfer them to qPCR cyclers. So what is important for a cycler? And from my perspective, it's several things. It's first of all the flexibility for tubes and plates. I think it's a big plus if you have the option to work with different formats in the same device, so that you can put single tubes, 8 stripes, that you can put 96 well plates, and that for the plates it doesn't make any difference if they are skirted, semi-skirted, or non-skirted. But what I also think is very important, which is overlooked a lot of times, is the block homogeneity. I will come to that in a minute, and I think that controlled heating and cooling is a big advantage. A lot of times people talk about ramp rates, which sort of defines the speed of a cycler. I think yes, ramp rates are important. It highly depends on your application, but I personally don't think that ramp rates are the one and only thing to go for. I think that the other things that I've mentioned here are more important if you decide for a cycler. So what do I mean with block homogeneity? So you might know that the heating and cooling of a cycler is done by Peltier elements. So these are the things which are doing the heating and cooling. And this is the most technical slide that I have in my whole presentation. And there is two different ways to fix them. So you can have the heating area with a center fixing as depicted on the left-hand side, or you can have the heating area with a side fixing as depicted on the right-hand side. I can tell you that the Eppendorf Master Cycler X50 is using center fixing. What does it mean if we have a center fixed or side fixed element? So on top you see the center fixed elements. That means that due to the center fixing, there is only, if I jump back to that slide, there's only like a very teeny tiny spot in the very center of each of those elements where you don't have a perfect temperature homogeneity. That means, in consequence, that all of your samples running on that cycler, no matter if they are in the center of the well or at the edge, you will always get the same result because you will always get the exact temperature that you set. If we look at another cycler which is using side fixing, which you can see, these are the bands shown at the bottom, you can see that due to the side fixing, you have the so-called edge effect. So due to the fixing, you don't get the same heat performance at wells which are at the edge of a plate. The consequence is that you are losing quite some capacity on your plate, or even worse, if you don't know it, you are basically sacrificing samples or even sacrificing your whole experiments, because some of your most important samples, maybe controls, might not work because they are in a non-optimal position. The second thing is controlled heating and cooling. So if we talk about the ramping, if you reach a certain level, we talk about a temperature over and undershoot. That means that as a comparison, on the left-hand side you can see a Eppendorf cycler, on the right-hand side you can see another cycler. So if we say we want to heat the cycler to a temperature of 95 degrees, the Eppendorf cycler only has a very small overshoot of about 99 degrees, whereas the other cycler has a heavy overshoot of 107 degrees. So this will drastically decrease your enzyme half-life, and by that reducing your yield. At the same time, during the cooling, you can have an undershoot. So if you want to go to a temperature of 35 degrees, the Eppendorf cycler only undershoots to 32.5 degrees, whereas the other cycler undershoots quite heavily to 29 degrees, and this will give rise to non-specific bands. So that is like a very small thing which is often overlooked, but that can really make the difference for more complicated PCRs. So, and I've been talking for quite a while now, so I will come to a summary. So I hope you remember the slide that I've shown you in the very beginning with the whole process. So I will sum up what I have talked about so far. So if we take first a look at the process. So the most important thing, prepare master mixes. This is really key for a successful PCR. If you use manual pipettes, I would recommend to get yourself familiar with the technique of reverse pipetting, or switch to electronic pipettes. They make life much easier. Filter tips can save samples and nerves. And of course, I would always recommend to consider automation. Take a look at automation, think about it. Once you have it, you will never give it away, I promise. For the vessels, use the correct vessel size and shape for your experiment. As I said, no matter if it's plates or tubes, think about the heat transfer and think about the sturdiness. Choose the right purity for important experiments. So don't sacrifice your sample by using low quality consumables. Seals, I haven't talked about that very much, but seals can avoid night shifts, honestly. Nothing is more frustrating if you come back to the lab in the morning and you see that your seal was not tight and everything evaporated during the run. So check your seals, go with high quality seals, foils or lids. If you are not sure about the seal, do a test run just using water and running your PCR cycle with that seal. And if you consider automation, go for vessels which are suited for automation. So as I've shown you, the Eppendorf automation solutions, they are very flexible, but especially if you go for plates, look for a sturdy plate which can be grabbed by a robot arm. So for the cycler, I would always go for something which is flexible so that you can use different vessels, so may it be tubes or plates on the same cycler. A good block homogeneity lets you use a whole plate if you're using plate and not only half of it or so. And go for controlled heating and cooling for perfect results. And with that, I will come to my last two slides. I want to end with a citation of Kerry Mullis, the inventor of PCR, who recently passed away. And he said that sometimes in the morning when it's a good serve, I go out there and I don't feel like it's a bad word. And I know that working in the lab can sometimes be frustrating. If you don't get an experiment to work, it can be very frustrating. But with that, I wanted to end on a very positive and optimistic note, and be positive. Things will work out if you follow those tips and tricks. I'm pretty sure that you will get your experiment up and running and you will get really good results. And with that, I want to finish. I want to close the presenting part of this webinar, and I'm handing back to Christy for the moment.
Thank you, Tim, for that excellent presentation. Now, before we begin our live Q&A portion of the webinar, we'd love our audience participation in our final poll. We would like your answers, and your answers are very important to us, and they help us improve our webinar program. So, okay, let's get started on our Q&A portion. As a reminder, if you have a question you would like to ask Tim, please do so now. Just click on that Ask a Question box located on the far left of your screen. And any questions that we are not able to answer live today and those submitted during the on-demand period, Tim will be answering them via email at the email address you provided during the time of your registration. Okay, well, let's get started. Let's see, we've got some great questions coming in. Let's see, Tim, our first question, and this one has come in a couple times, is there any way to speed up a PCR?
That's actually a good question, and I would say that this is something which is highly situational. So there are ways to speed up a PCR. Sometimes you can use fast PCR reagents. So there are fast PCR enzymes and fast PCR other reagents. Another option is if you have a suited PCR, what we have at Eppendorf is so-called fast PCR consumables. These are only strips, and it's a very thin-walled material. So these work for certain PCRs where you can switch to this kind of plate. And here I have to come back to the ramp rates. Of course, ramp rates can make a difference. So if you have a cycler with high ramp rates where heating and cooling is very fast, you can speed up a PCR using this cycler. For the Eppendorf cycler, we have different block types. We have an aluminium block, which is already very fast, but for the high performance and also high throughput, we have a silver block cycler as well, because silver has very good heat transfer capabilities. You can go for a silver block cycler, and that makes it really fast.
Thank you, Tim. Now let's go with this next question. What is a technical replicate?
Good question. I mentioned that in one of my slides. The term of technical and biological replicate is something that I used during qPCR experiment, and I think it's sort of widespread, but sometimes people don't really know what it is. So for me, the best explanation is a biological replicate. So let's say you want to correlate the expression of a certain gene with a certain condition or with a certain set of donors. So a biological replicate would be to have several donors or blood samples where you suspect them to have the same treatment. That would be a biological replicate. Whereas a technical replicate is a sample that comes from one donor or one source and it's been split up into several portions. So let's say a triplicate or a duplicate. The reason why you're doing is that with the biological replicates, you are controlling your hypothesis, so your experimental hypothesis, whereas with your technical replicate, you are controlling your process. In this respect, let's say your pipetting, for example, or your precision in general.
Thank you for that clarification, Tim. Now, how do I know which settings to choose for my liquid when I am using a robot?
Yeah, that is also a pretty good question. So it brings me back to the slide, and maybe I can quickly go to that slide where I was showing different pipetting parameters. I think it's that slide. Yes. So first of all, yes, you can go with the presettings. That I think is the easiest way, at least for the Eppendorf system. So if you're using PCR premix, go for PCR premix. If you're using glycerol, go for glycerol. So, but then you can also change a lot of the parameters manually. So the aspiration speed, the dispensing speed, and stuff like that. And I have to tell you, to my understanding, it's not a very exact science. It is a little bit of trial and error, but there are some rules of thumb. So for example, if you have something which is very viscous, I would go for very slow aspiration speed and a very slow dispensing speed. And I would also use a blowout. So I would prefer a pipetting mode over a multi-dispense mode, because the blowout can kick out this last little bit of liquid from your tip. For example, if you work with something which is very volatile, I would always go for pre-wetting, because with this pre-wetting you avoid dripping with your of your liquid out of your tip. Anyhow, if you are not sure what are the best settings for your liquid, you can always come back to us, contact us here at Eppendorf. We have a test lab. We can even test that for you. so we can support you find the right settings.
Thank you, Tim. Now, what is a skirted plate?
I've mentioned that, right? I'm not entirely sure if this is a common, widespread term. So I learned it when I started here at Eppendorf, but that might also be a language thing, because as you might have noticed by now, I'm not a native speaker. So we distinguish between skirted or fully skirted, semi-skirted, or non-skirted plates. So a fully skirted plate is a plate which has this kind of collar around it, which reaches to the bottom. So basically, it has some sort of frame, and the frame has the same size as your valves. So if you are putting it on a flat tabletop, it will stand on both the tubes and the frame. This allows, for example, for using it in several devices without the need of an adapter. A semi-skirted plate has this sort of frame cut in half. So if you look from the side, you can see the wells, but it still has some sort of residual frame. It's one of the most common plates, for example, used for NGS library preparation. It has the advantage that it can carry more volume, but it can still be transported by a robot arm. And then we have a unskirted or non-skirted plate, and that basically means that it does not have any sort of frame. So if you look from the side, you can see the whole well. For a semi and a non-skirted plate, if you work with that on a robot, you usually need an adapter to securely place it on the deck. So, and this is what I mentioned if I talked about PCR cyclers. It depends. So there are some devices out there where you can only put one type of plate, so only non-skirted plates, let's say, right? So, and I would always prefer something which is independent of the shape of your, with the shape of your plate.
Now, Tim, while we're on the topic of plates, what is a better plate, the transparent or white?
Good question. It's not an easy answer. If you go for a regular PCR, it doesn't matter. So it can be transparent. It can be white. Because there is no actual detection step involved in that. If we talk about qPCR, there is a tendency to use a white plate because they do have better reflection purposes. In this respect, I personally would prefer a white plate, and if you go for a transparent plate, I would do a test run. Besides the plate, it's not only the plate which is important, it's also the seal. So for the seal, you usually need a very transparent, high quality, clear seal in order to do qPCR to get your best result.
Thank you, Tim. Now we're almost out of time, so we're going to wrap with this final question. How does automated normalization work?
Okay, that's actually something which I explained in the other sort of advertised webinar. In principle, the automated normalization works similar to what you would do manually. So you have, let's say, a certain number of samples, and you have a diluent. And then you will put the diluent and the samples together in a way that you end up with a plate where you have all of your samples having the exact same concentration. If you've ever done it, you know that this can be like super tedious and it's super error prone because you have to change the volume all the time. You have to go forth and back. So for automation, so at least for the Eppendorf solution, there are two ways. The first way, which I would not recommend, is to program it by hand. So you can start with your Excel sheet, let's say, or your handwritten sheet or whatever you have, and then you can program each and every step by hand, saying, okay, sample 1, I want to have 20 microliter of DNA and then add 30 microliter of diluent, let's say. The better way is to use a very easy CVS import function. So this works in a way that we would provide you with a special format Excel sheet where you can put in, let's say, your concentrations, maybe also coming straight from a measurement, and then you can decide how you want to normalize it. You want to have normalized volumes, you want to have normalized concentrations, and then you can save this file as a CSV file, and then you just have to import the CSV file into the automation software, and the system will automatically translate that CSV file into pipetting commands. By that, making it actually very convenient to deal with normalization, and especially with changing normalization every day. But it is pretty well explained in the webinar that I have mentioned on one of my previous slides.
Thank you, Tim. Now, before we go, I want to thank our audience for joining us today and for their interesting questions. And as a reminder, those questions we did not have time to answer today and those submitted during our on-demand period will be addressed by Dr. Schommartz via the contact information you provided at the time of registration. I would like to once again thank Dr. Tim Schommartz for his time today and his excellent presentation. We'd also like to thank LabRoots and our sponsor, Eppendorf, for underwriting today's educational webcast. This webcast can be viewed on demand. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. You will now be redirected to the registration page of our next webinar, From Cell Seeding to Analysis, Getting the Best Out of Your Cell-Based Assay, presented by Eppendorf's very own Dr. Jessica Wagner and Dr. Eric Bonke of Promega. This webinar will broadcast live on September 10th at 6 a.m. Pacific Time, 9 a.m. Eastern Time, and 3 p.m. CEST. We hope to see you there. So we say goodbye from Hamburg and California. Have a great day.